So up to last class, we have studied how to draw the different profiles of a cam and follower setup. Okay. If you are observing the profiles of the cams, we cannot see that it is having a circular path or it is having a straight line for the profile. And if you want to manufacture such type of profiles for giving a desired output, it is very difficult to manufacture such type of profiles or cams. So to avoid that, so we are going to analyze the cams. Instead of having different irregular shaped profiles, we are trying to analyze the cams with a curved shape, circular curved shape flanks, and as well as straight line curved shape flanks. Okay, so which gives more advantages or saving in the manufacturing cost, and the manufacturing of such types of cams also very easy when compared to the profiles what we have seen till now. Okay, so here in this analysis we are going to consider that instead of rotation of the cam, so we are rotating the follower. We are rotating the follower and we are analyzing the displacement of the follower, velocity of the follower, and acceleration of the follower. Okay, so for that we are having three different categories with the flat follower, circular R cam with the flat follower. Second one is tangential cam with the reciprocating roller follower. Roller follower. Third one, circular cam or circular arc cam with oscillating roller follower. So these are the three cases that we are considering in the analysis of the cams. So out of these three, so in our syllabus we are having the first one, circular arc cam with flat follower, and the second one, tangential cam with the reciprocating roller follower. So coming to the first one, circular arc cam with flat follower. With flat follower. So in this we are having two cases. The first case is contact of flat surface or flat face of follower at the contact circular flank and base circle. Base circle. That is, here in this figure you can see that this is the point where we are considering the contact between the flat follower and the cam with the circular flank. So the portion between the point, this point to N to E is the circular flank. This is called as circular flank. Parallel to this, we are having the portion M and the S. It is the circular flank. And the larger circle here with a radius equal to R1, it is called as base circle of the cap. Base circle or base radius of the cap. And the smaller circle, the radius R2, we will call it as the radius of the nose. The radius of the nose. Okay. And there is a second case in this. The second case is contact of flat face at any point on the nose. Any point on the nose. That is, this flat surface will be contact at this position. I will show that figure also. So this one. This is the second case. So now the first case is this one. So we are discussing about the first case. When the flat surface is in contact with the flank at a common point of both the base circle radius and as well as the flank R. That is, the base of this follower, the flat base of this follower, we will call it as common tangent to the both base minimum circle radius of the cam as well as the circular arc of the cam. Common point for the both this one. So this flat surface is perpendicular tangent to this circular arc and as well as this base circle. That is the position of the flat face follower on the circular arc cam. So in this we are considering that cam is stationary. Cam is stationary. Follower rotating. Cam is stationary. Follower is rotating. So follower rotating means, so here the solid line of the flat face follower in the initial position. So for a certain angle of displacement theta of the follower instead of cam of the follower is occupying a new position which is indicated with a dotted line. Follower is occupying. So here when there is a change in the position of the follower for an angular displacement of theta, we are going to observe that the displacement of the follower is taken from point A to B. Initial position is here at point B. When the follower is displaced for an angle of theta, it occupies a new position. When the follower is displacing, the point of contact having a change in the line of the stroke, so that indicates the displacement of the follower. This one as S. displacement of the follower. Now our objective in this is we need to find out how much amount of displacement is the follower is having. How much amount of displacement is the follower is having. So for that, from figure displacement of follower, that is the x, which is equal to AB, which is equal to AB. So this AB we can written as OB minus OA. AB can be written as OB minus OA. Okay, so this we call as displacement of the follower. Okay, for analysis, if you are observing or if you draw a line from the point O, it intersects the line drawn from the point of contact of the flat face follower and the circular flank. Okay, so here what is this C? C is the point of contact of the flat face follower and the circular flank. Okay, so in this, if you draw a line from this point C and it will meet the line which is nothing but equal to the line of stroke of the follower at point P. So the distance measured between the point P and the capital C, we'll call it as radius of the flank, that is capital R. So capital R is equal to radius of flank. So which is nothing but capital R we can define as CP. We can call it as CP. Or we can take it as PM also. Because where N is the point common for the nose circle and as well as the circular flank. Nose circle and circular flank. Okay. So similarly, on the opposite side of the top circular flank, we are having one more circular flank. We call it as M and S. And the center for this circular flank MS is P dash. P dash is the center for the circular flank MS, and it is also having the same radius. It is also having the same radius, which is nothing but equal to capital R. We call it as also M and S. Now, for analysis, if you draw a line from the point O, the line should be perpendicular to the line joining point P and point C. The line should be perpendicular to the line joining point P and C. So with this analysis, from this diagram, we can say that the line OB is always parallel to CD. As it is a rectangle. What is rectangle? Point B, point C, point D, and the point O is a rectangle. So from this rectangle, we can say that, or from figure we can say that OB is equal to C. OB is equal to C. Similarly, from the figure we can say that OA is equal to OE. OA is equal to OE. Why? Because A is a common point for point on the minimum radius circle. A is a point on the minimum radius circle. If you are observing this point E, this point E is also on the minimum radius circle. This one. Here this point E is also on the minimum radius circle. So with this we can say that OE is equal to OA because A and E are on the same circle and O is the center for the circle. Okay, so with this we can write that the displacement x is equal to, in place of OB it is CD, in place of OE it is. Okay, again from the diagram we can write that CD, that is PC minus D. PC minus D. PC, sorry, PC minus D. Can we write like that? CD का होगा PC minus D or PD. Okay, so it is what is meant by PC? What is meant by PC? It is the largest radius of the circular flank. Now PD we require or DP. PD or DP. Okay, write down here. Writing that CD is equal to PC minus DP. So we are observing the diagram. The distance from P and C. We are observing the diagram. The distance from P and C is equal to the distance from P and E. The distance from P and C is equal to the distance from P and E. Why? Because E is a common point for both the circular arc and as well as base circle. And C is a point on the circular flank. So because of that, we are going to say that CP is equal to PA. So therefore, the modified equation is PA minus D. PA minus D. Now, PA can be written as the sum of the distances OE and PE. PE can be written as OE plus OB. Now, CB is equal to OE plus OP minus D or P. So now the displacement x we can written as OE plus OP minus DP minus OE minus OE. So now from the figure from triangle POD, OD. This triangle. This one. Okay. From the triangle, cos theta is equal to adjacent side by hypotenuse. What is adjacent side? dp by hypotenuse OP. So from this, d3 is equal to OP into cos theta. So now the displacement x is equal to OE OP minus OP cos theta minus OE. So from this we can say that OE will get cancelled. Now x is equal to OP into 1 minus cos theta. What is OP? How we can write OP? OP is equal to PA minus OE or EO. Anything is correct. Now what is PA? Radius of the circular triangle. Okay, that is capital R. Minus what is OE? Radius of the base circle. Yes, radius of the base circle. That is R1. Now displacement of follower x is equal to, in place of OP, capital R minus small r1 into 1 minus cos theta. 1 minus cos theta. So let it be the equation 1. Okay. So this is the equation of the follower which can be satisfied when the follower moves for any angle theta and the point of contact is on the circular fact. This equation satisfies for the follower position at any angle of theta and the point of contact is on the circular arc fact. Now, if you differentiate this equation with respect to time, so we are going to get what is the velocity of the follower. Okay, so for that, so that is velocity of follower that is v is equal to, velocity is defined as rate of change of displacement with respect to time. That is dx by dt. Dx by dt. So which can be remodified as dx by d theta into d theta by dt, multiplying and dividing d theta by dt. Now we know that the angular velocity omega is equal to rate of change of angular displacement with respect to time dt. That is, the velocity v can be written as dx by dt is equal to into omega. Dx by dt is equal to omega. So that is the velocity v can be defined as omega into rate of change of displacement with respect to the angular displacement theta. Now we already determined what is the displacement of the follower, which is nothing but equal to x. Now the velocity v is equal to omega by d by d theta into r minus r1 into 1 minus cos theta. So that is omega into r minus 1 is a constant value into 0 minus cos theta differentiation minus sin theta into minus sin theta. So therefore the velocity v is equal to omega into r minus r1 into sin theta. So this is the velocity equation. So make it as equation number. What about the acceleration? What about the acceleration? So acceleration of follower A is equal to rate of change of velocity with respect to time t. So here also multiplying and dividing the equation with the d theta, that is d by dv by d theta into d theta by dt. So which is nothing but equal to dv by d theta into omega. D theta by dt is equal to omega. So that is the acceleration A is equal to omega into dv by d theta. Omega into dv by dt. Now we already know that what is omega. So therefore acceleration is equal to omega d by d theta into omega into r minus r1 into sin theta. So which is A is equal to omega square into r minus r1 into differentiation of sin theta. It is cos theta. So this is the equation 3. So all these three equations will satisfy at any point on the circular flank with a radius of capital R. That is, here we can say that the maximum angle that can be turned for half of the motion of the follower, it is pi, and minimum angle it is theta. Sorry, it is 0. That is, the above three equations depends on the angle theta. Depends upon the angle theta. So here theta. So theta varies from 0 to pi. Theta varies from
0 to
0 to pi. If theta is equal to 0, if theta is equal to 0, what is the velocity of the follower?
0.
Sin 0, 0. So that is theta is equal to 0. The velocity v is equal to how much?
0.
0. Okay. If theta is equal to 0, what is the acceleration A?
0.
Say acceleration A is cos theta. Cos 0. 1. So acceleration A is equal to omega square into r minus r1. So if theta is equal to pi, what is the velocity? V is equal to omega into r minus r1 sin pi, and acceleration A is equal to
Omega square into
omega square into
r minus
r minus r1
cos
cos
pi.
pi. Okay, so this is about analysis of a
Cam.
flat follower with a circular arc cam when there is a point of contact between the circular arc and as well as
This circle.
base circle with the flat face of the cam.